Hello ladies and gentlemen, we are going to just take a quick look at one more example of one of these slope fields problems, how to make a slope field and maybe how to extract meaning from these slope fields. So let me give you a differential equation. Y prime equals negative x over y. Again, there is some equation that satisfies this differential equation. I don't know what that equation is. In this last video, we actually knew the solution was one of the e to the x graphs. For this one, though, I don't know what the equation is that satisfies this differential equation. But at the very least, I can get a sense of what this is going to look like. I should say I should get a sense of what they are going to look like, because just like in the last example, there's probably going to be an infinite number of solutions for this differential equation. So let's take a look at a blank grid here and try to map a slope field. The slope field should represent all of the solutions to the given differential equation, which I will write over here. Y prime equals negative x over y. Y prime equals negative x over y. Alright, so how do we do this? First, we recognize that x, y are coordinates on a graph. X, y are coordinates on a graph, and this x right here and this y right here, that's what they refer to. They refer to coordinates on a graph. The y prime right here refers to the slope at any given point, the slope of an equation, the slope of a graph. Alright, so let's pick a point at random. Each of these points is going to have a little line segment associated with it. Each line segment is going to have a slope, and all together we're going to have a whole field full of slopes. That's going to be called slope field. Let's take a look at this point right here. How about the point 2, 1? According to the given differential equation, the slope at this point should be equal to negative x over y. In this example, the x is equal to 2 and the y is equal to 1. Therefore, the slope should be negative 2 over 1, which is negative 2. So the equation, the solution to this differential equation that goes through this point will have a slope of negative 2. I'm going to put it like that for now. How about this point right here? That's the point 1, 1. X equals 1, y equals 1. Y prime then, according to the differential equation, is going to be negative 1 over 1. So it's a negative slope still, but slightly less negative than the one before. The coordinates here are 0, 1. 0, 1. X equals 0, y equals 1. Y prime is negative 0 over 1. That's a horizontal slope right there. And let's go to negative 1, 1. Negative 1, 1. Whoopsie daisy. Okay, so let's go to negative 1, 1. And y prime there is going to be negative 1 over 1. That is going to be a positive slope. So positive 1. So this slope is going to change as we move from left to right. We could find the slope here. We can calculate it at negative 2, 1. And we'll find that the slope is 2. The slope over here at negative 3, 1 is going to be 3. As we move farther and farther to the left, our slopes are going to get steeper and steeper and steeper. So here we go. Here's a good representation. Over here, the same thing's going to happen. At the point 3, 1, for instance, our slope, our derivative, is going to be negative 3 over 1, which is negative 3. So this is going to start getting steeper and steeper and steeper. We're going to start seeing a pattern that emerges. One issue that you might run into, however, especially when the differential equation involves some sort of ratio, some sort of quotient, is how about this point? 2, 0. 2, 0. Well, the derivative at 2, 0 should be equal to negative 2 over 0, which of course is undefined. And this has happened before. We've definitely dealt with graphs where the slope was undefined. Consider this graph right here, actually. Yeah, let's do that graph. That's a great graph, Mr. Mayhew. How about the graph of a circle? So at the top of the circle, the slope is 0, but on the right side of the circle, right here, that slope is actually undefined. It's vertical. There's no rise over run that could possibly describe that slope. So something like that is happening in this problem. Let's just do a few more, and then I'll press pause and I'll map the entire slope field. And let's go down here. Let's go to 2, 1. So we're going to go below the x-axis. That's not 2, 1, that's 2, negative 1. According to the differential equation, negative 2 over negative 1, we are going to get a slope of positive 2 right there. Positive 2, this is going to be positive 3, positive 4, positive 5. Steeper, steeper, steeper. This is going to be positive 1. This will end up being 0 also. In fact, all the points on the y-axis, where x is equal to 0, besides this middle one, where y is also equal to 0, all of those slopes are going to be 0, because we have 0 over y. So I can go ahead and fill these in right now. Okay, well, give me a moment, and I'll fill in the rest of these. Hold, please. And voila! There we have a completed slope field. This is a collection of slopes that satisfy the differential equation. And if I weren't mistaken, call me crazy, but what it really seems like we're dealing with here are graphs that are circles. So here maybe is an equation that satisfies the differential equation. Maybe this is another equation. We're just following the slopes all the way around. The slopes kind of point the direction. They kind of help shape the graph. So these slopes are pointing me this way. Round and round they go. All of these circles, it seems, satisfy the given equation. And we can actually algebraically confirm that real quick. All of these circles seem to be centered at 0, 0. Well, the general equation in terms of x and y of a circle centered in the middle of a graph is x squared plus y squared equals r squared. If we were to differentiate this equation in order to find y prime, we would use implicit differentiation. So let's see what happens when we take a circle equation and we derive the entire equation in terms of x. So this first part becomes 2x. Maybe just to remind you how to do this process, it's helpful to think of y as f of x. So we're squaring f of x. When we write it like that, it's easy to see, or easier to see, that we have a chain rule happening. So this becomes 2x plus, and if we apply the chain rule, the outside function is x squared. So we take the derivative of x squared, which is 2x, plug in the inside function, and then multiply by a derivative of the inside function. And this is going to be equal to 0. R squared is just a number. It is not a function or anything like that. Think of that R squared as just like a big capital C. So what we do now, 2x plus 2. Let's go back to our y notation. Y times y prime, hello, equals 0. If we clean this up and try to isolate y prime, we get 2y prime equals negative 2x. Divide both sides by 2y, we're going to get y prime equals negative 2x over 2y. And sure enough, our hunch was correct. I didn't know what equation was going to satisfy this differential equation, but I made a slope field, and it sure looked like all those slopes were coming together to make a circle. I followed the hunch. I gave the general equation for a circle. I used implicit differentiation to define y prime, and sure enough, it matches up with the original differential function. Y prime is equal to negative x over y. So there's the second example. I hope this has furthered your understanding of this mysterious thing called a sloped field. Goodbye.